Well, good morning, ladies and gentlemen. So today we are celebrating the first decade of the Orbitrap mass spectrometry, and I will try to make a bridge from celebrating Orbitrap to what we are going to celebrate starting from tomorrow, which will be completion of human proteome, and we'll see how it goes. So Orbitrap is 10 years old, and over these years it built a highway and railway in the land of ultra high resolution. And as we all know, high resolution provides selectivity of analysis, and accurate mass provides low error rate and improves accuracy of analysis. And it's all started a long time ago. But by this time, there were already many other mass analyzers heavily used in the field. And here I put them all together, showing their sort of inherent properties, their instrumentome, all collection of their properties. So here we have the first ones, magnetic sectors, which I'm not expanding on because they're just selecting single mass at a time. We have quadrupoles, also more like mass selectors. And then we have these three analyzers, which are capable of addressing the entire mass range. And therefore, these analyzers are most widely used in biological mass spectrometry. And so if you look at properties of each of those analyzers, we will see that each of them has its own combination of analytical properties. For example, FTICR has extremely high resolving power, mass accuracy, good dynamic range, but not so great transmission, pretty low speed, and it definitely lacks simplicity. On the other hand, ion traps have very high simplicity. They have extremely high transmission, reasonable dynamic range, speed, but quite limited resolving power and even more limited mass accuracy. And this all results in limited quantitation capabilities. And then we have time of flight, which has extremely high speed, also detects all ions, but suffers from limited transmission, and nowadays it has pretty high resolving power, but because of this limited transmission, we are also limited on the quantitation side, and they're not simple anymore. And so if you want to build on the basis of these analyzers, then we should take the best from each of them. And this is exactly what happened. So from ion traps, we took trapping in the field created by super accurately shaped electrodes. From FTICR, we took image current detection, and from time of flight, we took pulsed injection into electrostatic fields. And what we got is this combination of several distinctly different units, which are all united in a single Orbitrap analyzer. So we have external pulsed ion source, we have electrodynamic squeezing in the Orbitrap, trapping, and image current detection. And currently, this whole system works in the following way, that as external pulsed ion source, we use a bent quadrupole, which is filled with gas, and ions enter this bent quadrupole along the axis. They lose energy in collisions, get trapped, and then RF on the rods is removed, and the field is applied across this quadrupole. So ions are forced to fly through the lens system, get to the entrance of the Orbitrap as a very short packet. And then, as ions enter the trap of equator, voltage is increasing on the central electrode. And by doing this, it forces ions to squeeze towards the central electrode, and then voltage ramp stops, and ions get trapped inside this volume. As every packet of ions contains thousands and thousands of different ions, they all spread around the circle, forming those rings. And then we are detecting oscillations of those rings using differential amplifier. And as the ring goes back and forward, we get sinusoidal signal on the output of amplifier. For multiple signals, we have superposition of multiple sinusoids, and we could deduce all frequencies here and hence masses just by inverse Fourier transform. And this is the very first commercial instrument where this was all implemented, as you know. So here we have linear Eintrap on the front here, and linear Eintrap is responsible for producing ions, delivering them through atmospheric to vacuum interface, and then processing ions in the trap. They could be isolated, fragmented, and so on. In any case, they are stored near the exit of the linear trap and held by this voltage barrier. And then voltage is released, ions are allowed to flow to our band quadrupole, the C-trap, and then it all happens as in the previous slide. They get squeezed and then they get released towards the Orbitrap analyzer. And the important feature of this instrument, which was not obvious at the beginning, became very high transmission of ions from the Eintrap to the final signal. So currently it reaches 30 to 50%, which is one order or even two orders higher of magnitude higher than in all other accurate mass analyzers. And this single parameter, along of course with built-in properties of high mass accuracy, resolution, and so on, enforced acceptance of this instrument in proteomics. So if you compare this Orbitrap analyzer now with those original analyzers, we could see that indeed it has a lot of common with both FTICR and TOF MS. Like in FTICR, we trap ions in ultra-high vacuum, we use image current detection, Fourier transform, we have very high kinetic energy during detection, and we require extremely long mean-free path. So currently we could easily have mean-free path of ions in hundreds of kilometers before they collide with the next molecule of residual gas. And what is important is, of course, that resolving power depends on the detection time, but dynamic range is only weakly dependent on the detection time. In the same way as in time of flight, Orbitrap utilizes motion in electrostatic fields, which provides potential, which is independent on the mass-to-charge ratio. It utilizes high-energy injection, and if fragmentation takes place, then energy spread is extremely high. And because of this commonality, we have period of oscillations dependent not on mass-to-charge ratio like in FTICR, but on square root, which allows to provide flatter dependence of resolution on mass. And in time of flight, resolution is constant as opposed to the Orbitrap, but drawback is that if you have short acquisition time, then your dynamic range also reduced proportionally. And unique feature of the Orbitrap analyzer, which distinguishes from both, is that we excite oscillations just by injecting ions off equator in the trap. And this we use for enhanced Fourier transform and other modern processing methods. Another way to present this feature could be to compare what will be the maximum rate of MSMS if we are limited by the ion current into our system. And we could see here that even though time of flight could run at a much higher speed, it requires much more ions to get meaningful MSMS spectrum. And therefore, if we don't have sufficient flow of ions into time of flight, we will not be able to get high number of MSMS spectra per second. So, since original introduction in 2005, there were many improvements on all parts of the technology. There were a couple of generations of C-trap. There was additional fragmentation in the form of higher energy collision-induced dissociation in a dedicated collision cell, then electron transfer dissociation, later electron transfer dissociation combined with HCD. We had S-lens to improve the performance of the ion source. And so here you could see how each of those crucial analytical parameters was developing with time. And of course, each time we were introducing a new instrument to enforce these features. And one of the most important ones became the throughput of analysis, because Orbitrap started from its image current origins and originally was relatively slow, and therefore we put a lot of effort to increase just throughput. So first, the original trap, which had 30 millimeter diameter, is increasingly replaced by compact high field Orbitrap, which allows to almost double the acquisition rate. And then new signal processing method utilizes the synchronization of ions as they get injected into the Orbitrap, and this allows to double acquisition rate. And now we also use pipelining between filling the C-trap and detecting ions in the Orbitrap. We could do this now in parallel, and this allows to save time, sometimes up to the factor of 2. And this all allows to improve the throughput of the system. And here we come to one of the long-standing discussions which we had almost from the beginning of the Orbitrap mass spectrometry, that we have a slow analyzer, and there are other analyzers like time of flight which are much, much faster. And here we could come back to the ancient 1,000 years old discussion, haste versus speed. So if we are very fast but run into haste, then in the end we will get very little speed. And to explain this, let's consider an analogy, like a big conference where we have a lot of postgraduate students, for example, and then we have a single dispenser of highly desired drink. And then we have two ways of dispensing this. So we could have just disposable spoons, which are very small and could hardly quench thirst of all these people, but we could fill them extremely fast. And we could serve a lot of people, but all of them will be quite unhappy because they will get so little. And because we have powerful tap, most of this liquid will be thrown away. Or the other way is to have large glasses and then fill them with minimum losses and get high satisfaction of people. And so these are two approaches, and basically this is the one which we chose. And as you could see, for mass spectrometry, not always you could throw away most of the ions. And so this is sort of analogy which we could apply to the acquisition in the Orbitrap mass spectrometry. So we try to preserve as many as possible of our ions and utilize them to the best. And in this way, we are replacing haste with speed. But of course, with time, tap becomes stronger and stronger. Our ion sources deliver more and more ions. So our glasses also need to move faster and faster. And this is what was happening over all these years. So as we started with LTQ Orbitrap, we were able to have about 5 parallel scans in the linear trap at nominal mass resolution, and only 1 or 1.5 data-dependent scans in the Orbitrap in 1 second. And then we increased the number of scans in the linear trap, but real breakthrough came with the introduction of Exactive, when we focused on getting many high-quality, high-resolution MS scans in the Orbitrap analyzer. And there we were able to raise it to 8 to 10 data-dependent scans per second, in addition to the full MS scan. And then with the new instruments, we are able to go to 20 or 25 data-dependent scans together with full MS scan in 1 second. And hopefully we could continue increasing this throughput. So as a result, we could serve more and more MS scans and provide more and more identifications per second. And so, as a result, we have now Orbitrap mass spectrometry as a powerful tree with a trunk as the analyzer, roots in all types of liquid separations, and the tree itself went through many steps of evolution. So many of original instruments are not produced anymore, and now we have just 3 major families of instruments. The latest representatives of the original LTQ Orbitrap family, with Orbitrap Elite as the top tier. Then our family of benchtop instruments, co-exectives, and new family Orbitrap Fusion. So I will quickly go through each of them just to show where we are developing them currently. So for Orbitrap Elite, this is now a relatively ancient instrument, 4 years old. So this is where you could see how it changed comparing to the original LTQ Orbitrap instrument. So instead of the tube lens interface, we have a ref lens here of the similar to funnel type. We have dual trap instead of single for fast analysis, and we have freedom of fragmentation. CAD, HCD, ETD, all of them could be carried out in this analyzer. And then we have modern compact high-field Orbitrap analyzer with EFT, which allow to increase the resolving power in 1 second. And this instrument has the best pumping out of all systems which we have, and this we use to play with the extreme performance of the Orbitrap analyzer. Like, for example, getting resolving powers beyond 1 million, and then using them, for example, for element counting, because from this fine structure of this little isotope, we could basically count how many sulfurs, oxygens, nitrogens we have in the elemental formula of this molecule. Or with playing with the gas in the cell and so on, it was possible to get isotopic resolution up to intact antibodies and at 150,000 Daltons. But this, of course, required very long transients and very good pumping of the system. And so now we come to the top tier representatives of the Orbitrap family, which actually brings a new word to mass spectrometry. And this new word is tribrid. So Orbitrap Fusion is a tribrid, which means a combination of 3 mass analyzers. And of course, it's much more complex than just 3 analyzers. This is an entire orchestra of different devices where analyzers are first fiddles, but there are also many, many other new players. And so, from analyzers point of view, we have basically the best representatives of each class. Hyperbolic rod quadrupole with high mass capability and narrow isolation width, and dual pressure linear trap with isolation down to 0.2 Thomsons and high scan rate, and Orbitrap analyzer, which is currently spec'd up to 500,000 or 18 Hz, but we should expect that both of these ends will expand in future. And there are many, many different applications of this instrument which merit another hour of lecturing, but I would just mention the most widely used, widely followed applications, like application of Orbitrap Fusion for analysis of whole proteome, for glycoproteomics, for phosphorylation, lipidomics, cross-linking, and antibodies, and so on. And with every month, we hear about more and more of different applications. Another instrument which is the most mass-produced currently is co-executive family. So here we have a relatively simple instrument where we have top-of-the-range RF lens interface, quadrupole mass filter, and our standard Orbitrap analyzer, which utilizes enhanced Fourier transform and parallel filling detection. So the idea was to make a simple instrument, the one you could build from Lego. And so here Originally, it was planned for small molecules. Therefore, we are having here piglets and not elephants. But situation changes. So first, we get our wet piglet into vacuum, and then it sails around the corner in this bent flatter pole, and then passes on the edge through quadrupole mass filter, and finally we get him already dry and pink in the C-trap. And now you could see that piglet is very anxious because now he has to go down. But he is pushed down, and then we listen to his oink oink as it travels inside the Orbitrap. So this was the original intention of this instrument, but since then we built on its success into a whole family, which Ken showed before, but I sort of had liberty to add these pictograms, how we could consider these instruments. So our Pony Exactive Plus, in fact, grew up to address not only piglets, but also huge elephants in the form of protein complexes. Coexactive Focus is our heavy lifter for routine analysis in environmental food and safety applications. Coexactive Plus is the real workhorse all round for all types of applications. And Coexactive HF is also our heavy-duty racing horse. And so this is where one of the most heavily discussed currently themes come very relevant. So most of these devices are used not only for qualitative analysis, but also for quantitation. But as you remember, in this instrument we have not one, but two traps. We have C-trap and we have Orbitrap. And everybody in his right mind, would say that it's not possible to do quantitation in traps. But if we address this scientifically and look what actually quantitation requires, then we could split it into several important issues. We need very high linearity between the output signal and input. We need high discriminating power, high dynamic range, low limits for quantitation, and compatibility with modern high-speed separations. And when we started, we lacked a lot of features there. So fortunately, we had high transmission in the system and high sensitivity of detection due to modern electronics. We had high ion capacity of the Orbitrap analyzer, linear detection system, and high resolution, but we lacked all these features. And so the first precise control over input-dependent effects was provided by the linear trap analyzer. And this also allowed to ensure high mass accuracy. So quality of AGC is very important for both of these features. And then our ability to fill C-trap in parallel to the Orbitrap analysis in different modes with multiplexing or not allowed to open several new modes of operation, which I will show later. And then increased throughput of the detection and decoupling of detection from the filling of the C-trap allowed to interface Orbitrap not only to LC, but also ultra-high performance LC separations. And basically, this means that now it is time for Orbitrap quantitation. And so, if you just look how Orbitrap could compare to our basic workhorse, which is triple quadrupole, we should, of course, run some hypothetical experiment. For example, when we have one precursor, which then is split into n fragments of equal intensity. And now we try to see how many ions of precursor do we need to spend in order to get 10% CV on the sum of all these fragments. And so if we start from triple quadrupole mass spectrometer and we have just one channel of fragmentation, then with all transmission losses and so on in the quadrupole, we don't need many ions. We need probably a couple of hundred ions in order to get 10% CV on statistically limited for this channel of fragmentation. But if you have two channels, then we need to switch between 1 and 2. So we need twice more ions. If you have n channel, we need to split between n channels. And therefore, the number of precursor ions which we require goes linearly with the number of channels which we follow. As opposed to this, Orbitrap requires more ions to detect just signal, because image current detection is not as sensitive as single ion detection in triple quadrupole, but it detects all fragments in parallel, and therefore, as we increase number of channels, the number of ions required from the source is actually not growing so dramatically. And the same is true for time of flight, but there, because of orthogonal acceleration, we start from much higher level due to lower transmission. And this basically shows that somewhere around 3-4 channels for quantitation, Orbitrap becomes even more sensitive than triple quadrupoles, even without taking into account all advantages of high resolution, mass accuracy, and so on. And this is what we currently observe in the field of peptide quantitation, where more like 4 to 6 fragments are needed in order to quantify the precursor. And actually, all these different ways of operating with ions allow to explore different quantitation strategies with the Orbitrap mass spectrometry. Unfortunately, there is no one-size-fits-all, because we have huge variety of samples, which come from low complexity samples of low dynamic range, usually due to very high quality of separation, down to very complex samples with over very high dynamic range, which is usually meaning that there is not sufficient separation. And we have analytes which could span over many orders of magnitude from low abundance to high abundance. So if you talk about samples of low and medium complexity, then even full MS would allow to quantitate in parallel thousands of channels, thousands of different peaks. But as we increase our complexity, we run out of the dynamic range for full MS. And this is where other methods like data-independent acquisition could help, because they allow to split this full mass range into multiple mass ranges and follow each of them separately. But of course, because you follow only one part of mass range, you could follow a bit less channels per the same time. And there are several different strategies for data-independent acquisitions. These two are possible in all Orbitrap instruments, and this wide seam DIA is specific to fusion instrument. And then, as we go to more and more complex samples, this is where selected ion monitoring becomes more appropriate, because it allows to target really low abundant species, but of course number of channels which could be followed drops. And it further drops as we go to the most low abundant species in the most complex matrices. This is where targeted MSMS or multiplexed MSMS is the most appropriate. And so depending on the sample, different methods become more appropriate for quantitation. And as a result, this is the universe of different applications for the coexactive family, as Ken mentioned, starting from a lot of applications for drug screening, anti-doping, pesticide analysis, and so on, and of course for peptide quantitation, for both in artificial samples and real plasma and so on. And using the simplest of those instruments, the Exactive without any quadrupole, we explored how far could we push it from the point of view of mass to charge ratio. And this is currently the highest record which we could get from mass to charge ratio point of view. So up to 40,000 could be still detected with the Orbitrap analyzer. And this could be used for analysis of larger and larger molecules, as you could see results of our collaboration with Albert Hecht's group, where viruses up to 4.5 megadaltons were detected using Orbitrap mass spectrometry. And image current detection brings high resolution, because we don't need to convert ions into secondary particles. Therefore, we could get higher resolution of detection, and this allows to separate different forms of viral particles. And this continues to be an area of active research. And of course, here we come to the celebration which we are going to have tomorrow, which is completion of human proteome. And this, of course, rings the bell in connection with the original celebration of human genome completion back in the year 2000. And now, many years later, we have two papers, some of authors are sitting here, which show the completion of the first draft of human proteome, and both teams base their studies on the Orbitrap mass spectrometry. And with this, I'm coming to conclusion. So this is where we have started many years ago, looking at biological systems. And then high resolution provided detail to this picture, and MS sensitivity gave color to it. And now improved quantitation capabilities and throughput of the instruments allows us to observe biological systems in dynamics. And further progress will be based on increasingly intelligent utilization of the CTRAP and Orbitrap capabilities in combination with other mass analyzers. And finally, I would like to present the team which is now powering this whole development and marketing of the entire Orbitrap family. And thank you very much for your attention.